Hello everyone, welcome back to a new lecture on electricity and magnetism. And today we are having the most interesting topic as well as the most important topic on electromagnetism, namely the Maxwell's equation. So any first level course on electromagnetism will always almost end up with the establishment of the Maxwell's equation, the meaning of this equation, and how Maxwell has arrived at these equations. And finally, the electromagnetic wave equation can be established from this, and that would be the place where the first level course on electromagnetism will come to an end typically. And the second level course on electromagnetism will deal with the solution of the Maxwell's equation. Okay, Maxwell's equations are, by the way, differential equations, and therefore the solution of the Maxwell's equation would be one of the main objectives in the second level course on electromagnetism. And generally the second level course is known as either electrodynamics or electromagnetic theory. So the objective is therefore different in second level course, namely the boundary value problems in electromagnetism, and then the solution of the electromagnetic wave equation, that means how the electromagnetic wave is propagating. And then we will also, the second level course will also deal with the transmission lines, a basic theory of antennas, and these are the typical course on a second level course. And therefore, and in particular, some of the physics courses will include a course on or a topic on relativistic electromagnetism. Okay, but otherwise in general, engineering departments will have more emphasis on the antenna theory and then the electromagnetic wave propagation in rectangular waveguides. Okay, and then this will lead to ultimately fiber optics theory. So the topics will be going depending on the interest, whether it is pure science or applied science. So the idea about the Maxwell equation, it is the central theme in the electromagnetism, and therefore this happens to be the very important topic also. So we are now going to see that in continuation with the previous lecture, namely that was the lecture number 26. So what are we going to do is that this is the starting point of writing down the Maxwell's equation, and in today's lecture and in continuation with this particular lecture, we will be dealing with the derivation of the appropriate Maxwell's equations starting from the basic experimental observations. Especially in the last class, we have seen the Gauss divergence theorem, and from that Gauss divergence theorem, we have rewritten the differential form of the Gauss law to the integral form of the Gauss law. And after that, we have also seen what is the application of the Gauss law, namely to calculate the electric field. So the point should be clear. Electric field can be calculated both by using the Coulomb's law as well as by using the Gauss law. So when to use Gauss law and when to use Coulomb law should be clear to you. So the point is already explained in the last class, but let me tell the summary. Gauss law is useful only when the physical systems under consideration exhibit certain physical symmetry, certain geometrical symmetry. That means either you should have spherical symmetry, cylindrical symmetry, or some kind of rectangular box-like thing. Some coordinate system should be applicable to the problem under consideration. Okay, that kind of symmetry, if it is present, then Gauss law will help to a great extent in calculating the electric field. That is the place where Gauss law enters into picture and gains its importance. Suppose if the physical system doesn't have any of these special symmetries, then Gauss law is not of much use, and therefore you have to revert back to the Coulomb's law itself, and then you'll have to calculate the electric field by whatever equation that is there in the Coulomb's law. So that is the distinction between in which situation you have to use Coulomb's law and in which situation you have to use the Gauss law. So that clarity should be there. That is the clarity lies on the symmetry of the physical system. So let me therefore write down what we have done in the last class, especially the equation that is established for the Gauss law is written down as the divergence of the electric field is equal to you have the rho divided by epsilon 0. This is the differential form of the Gauss law. So let me therefore write down that this is the Gauss law in electrostatics, or we say that this is the Gauss law in electromagnetism, and the same equation is what is known as the Maxwell's equation. So I'll write down that this is the Maxwell's equation number 1. We are going to have 4 of this equation. So ultimately, number of Maxwell's equation is 4. So out of the 4, we have already established one of them, namely this divergence of E equal to rho by epsilon naught. You can write down the Maxwell's equation in 2 different ways. One is in the differential notation. The other one will be in the integral notation. So there will be 2 versions are there. Therefore, we will also write down that the same Maxwell's equation 1 can also be rewritten as, that's why I have written this particular equivalent to symbol. This is also equivalent to writing the integral E dot ds will be equal to Q enclosed. So ENC means enclosed divided by epsilon 0, where the integral is a surface integration. So you are going to perform the surface integration, and the details of the meaning of this is already explained in the last class. So the conclusion, or what is that we are trying to say here, is that we have already established one of the Maxwell's equation, namely out of the 4, you already know one of them. Whether you write in the differential notation like this or in this particular integral notation, they are identically same. Okay, they are identically same. It is only some of the times one of the versions will be comfortable. That's all about it. So now that this is clear to you, what are the other equations? What are the remaining 3 equations? That is the question that comes. And interestingly, even before doing the calculation, we can imagine what are the possible equations. So let me therefore write down what are the possible equations, or what are the other equations going to be, how they are going to look like. That can be seen, and then we will see how to obtain them. Now, in the case of the electromagnetic theory, we are going to have the electric field and magnetic field. That's all. These are the 2 fields that are there in electromagnetism, and these are the effect. Effect means because of something this is happening. Because of what electric field is coming is because of the stationary charges. And similarly, because of the electrical current, you will be having the magnetic field. So the sources are there. The sources are the charge density rho, and then the current density J. So rho is a scalar quantity, J is a vector quantity. So these 2 things are the sources that we are going to have. And then these 2 things will be the effect, or we say that cause and effect relation, like that we can say. And therefore we will be having the fields here. So this is the cause. We can say that these are the cause, and which means that this will be the effect. So now where will you observe the fields and where will you observe the source in the equation? If you see, you can always see that on the left hand side of the equation, you will be having the fields, electric field or magnetic field. You'll be having here. On the right hand side, you will either see the time, if at all there is a time dependence is there, you will be see, or you will be seeing only the sources. Okay, if at all there is a effect on the source is there, dependence of the source is there, you will be able to see that. So in general, remember that the source terms will be present on the right hand side, and on the left hand side we will be writing down the field terms. This is the first point. And second point is, in terms of mathematics, whenever the source terms are present, the equations are known as inhomogeneous differential equation. So let me write down that if the source terms are present, that is what I am writing here. This implies means if the source terms are present, then we say that the corresponding differential equation will be an inhomogeneous differential equation. So naturally you can see that the divergence of E equal to rho by epsilon naught, which is the Gauss law, and Gauss law is identically same as the Maxwell's first equation. And that happens to be an inhomogeneous differential equation because of the existence of the source terms on the right hand side. Suppose if it is 0, then it becomes homogeneous differential equation. So we can therefore write down as a special situation that in the case of vacuum, suppose if you are going to discuss the electric field in vacuum, where the charges are absent. Okay, we are going to see later. So right now, let us not enter into the detail, but later we are going to see that in the vacuum, if we are going to discuss the electric field in vacuum, where the charges are where the charges are absent, in such a situation, we can write down that the divergence of E will be equal to 0. So why this has become 0 is because the charge density rho has become 0. Epsilon naught, of course, nothing happens. That will be there. So basically, this is 0 divided by epsilon naught, and therefore divergence of E will become 0 in special situation of vacuum only. Okay, not in other places. So whenever you don't have the charges in that particular region, then the corresponding equation will become divergence of E equal to 0. So this equation is also again it's the same Maxwell's equation taking the special situation or a special case. So this particular equation is then known as the homogeneous differential equation. So I want to distinguish between homogeneous and inhomogeneous differential equation by looking at the right hand side and by looking whether the source terms are present. Source term means either it can be the charge density rho or it can be the current density J. Any one of them. If any one of them is present on the right hand side, then the corresponding equation is mathematically classified as inhomogeneous if it is present, and if nothing is present, then it is known as homogeneous differential equation. So that is fine. Now that we have the first Maxwell's equation, the next question naturally comes: what will be the other Maxwell's equation and how are they going to look like? So that clarity should be there. Then we will be able to proceed further. So as I already told you that we will be having either the electric field or the magnetic field. These are the two options in the case of electromagnetic theory. And in the vector calculus, if you see, we have two operators. One is known as the divergence operator. Divergence operator means del dot. And then the curl operator. Curl operator is del cross. So this is what we say curl operator. And this is the divergence operator, we say div. If you write like this without dot and without cross, then this is known as the gradient operator. And remember that the gradient operator will work only on scalar. So gradient can be performed only on a scalar, whereas divergence can be performed on a vector. Curl can be performed on a vector. So that should be clear to you. Okay, only when it is clear, now we can understand what it is. Now these two quantities are vector quantities. So you tell me whether divergence is possible, curl is possible, or gradient is possible. Possible means which one you can perform. Can you perform the gradient operator on electric field? No, you can't perform because gradient can be performed on a scalar only, so not possible. Can you perform curl operation? Yes, possible, because curl can be performed on vector. Similarly, divergence operation can be performed on a vector. So these two operations are possible. So if it is possible like that, then you are going to have two possibilities here. So let me write down that if you are going to perform the divergence operator, then I will be having divergence of electric field. In case if you are going to choose the curl operation, then I can perform the curl operator on the electric field. Then I can have this. And the same thing is true even in the case of the magnetic field. So if I am going to choose the divergence operation, I will be having the divergence of the magnetic field. If I am going to perform the curl operation, then I can have a curl of the magnetic field. So it is clear that these are the four possibilities that you can perform mathematically. Okay, there is no physics involved here. Mathematically speaking, we have two differential operators and we have two vector quantities. So naturally, these are the possible combinations that you can perform, and you cannot perform the gradient of an electric field. Such a thing is meaningless, and there is no point in writing like this. So therefore, such things there is no need to worry. Now you see how many options are there. So that will be your first Maxwell's equation. So now you can understand why Maxwell's equation, 4 of them are there. So it doesn't matter which is known as 1, 2, 3, 4, but generally people say that okay, let us combine divergence first and curl separately. Then the first equation is known as the divergence of electric field. Then this will be the second equation, second Maxwell's equation. Then this will be the third Maxwell's equation. That will be the fourth Maxwell's equation. Which means that the idea is that first you finish the divergence. That is why it is called 1 and 2. So 1 and 2 is you are finishing the divergence. Then you are coming to the curl. Then curl again you do 2 of them. So 1, 2, 3, 4, that is the order in which you can do. But this order is not very important. There are only 4 equations are there. That is very important. Now these are the quantities that you can perform. But this is not equation. You see, del dot E is not an equation. Del dot E should be equal to how much? That you have to tell. Then only it is an equation. Similarly, if you say curl of E is not equation. Curl of E is equal to how much? Divergence of B equal to how much? So you have to calculate. So therefore, you will have to finish this calculation. Divergence of E equal to how much? This is the place where you have to perform and complete your calculation. And if you do that, then only it becomes an equation. Now we can say that this is equation number 1 and this is equation number 2. This itself is not an equation. Okay, so that should be clear. And already we have finished one of them, namely that this is equal to rho by epsilon naught. We have already seen. And in the last class or the previous class, I have also explained you that the divergence of the magnetic field is equal to 0. And this is observed from experimentally from the magnetic field lines. You know what do you mean by a solenoidal field? This is called solenoidal field. I explained, I think, previous class or one class before the previous class, where I explained that the magnetic field lines are closed loop. Whenever it is having a closed loop field lines, then the corresponding divergence will be equal to 0. So therefore, that will be the second Maxwell's equation. And we will have to establish 2 more equations, namely how much is this and how much is this. So if you are able to do these 2 things, then we will be having the remaining third and the fourth equation. So objective should be clear. I am explaining this because you should know what we are planning to do and what is the purpose of doing certain equations or bringing certain points into picture. Okay, and in the previous class, I believe that I have also written down this particular expression minus dou B by dou T. In one of the previous classes, I said that this is the Faraday's law. Okay, so this happens to be the Faraday's law, and this is the expression coming from the closed structure of the magnetic field lines. And let us see some more details on these topics today. So our conclusion or our overall idea, now it should be clear to you that we are going to have, of course, this is the one which we are going to calculate and write down. We'll do that. So ultimately we are going to have 4 equations, and this particular set of all equations, the entire set of all 4 equations are known as the Maxwell's equations in the case of electromagnetism. But we are going to do certain detailed information about this, and then we will say why they are known as the Maxwell's equation. Why they are known, of course, the reason is Maxwell has carried out all this, explored the vector calculus properties and applied it to the electric and magnetic fields, which are the experimental data that is available from Coulomb's law, Biot-Savart law, Faraday's law, etc. Okay, so Maxwell has taken all this experimental information and then written down the equation based on the rules of the vector calculus, and ultimately it has led to certain interesting equation. And this set of 4 equation is the one that is responsible for the development of the electromagnetic wave equation. So we can now derive from these 4 equations, we can derive electromagnetic wave equation. So I think that portion we will see in the next class. Okay, electromagnetic wave equation we can derive from these 4 equations. That we will do later, because let us first complete this 1 to 4 and how this is coming, and how actually we can write down these 2 things, 0 here and then minus dou B by dou T. So that is our today's objective. So objective should be clear what we are doing, and the operators are very clear to you, divergence and curl operator. So that is clear. And remember, this first one we have completed and with some details. And the first equation has connection with the Gauss divergence theorem. That also you should remember. Exactly last class we have done. So now let us see how we can perform some additional calculation in order to establish the second equation, third and the fourth equation. So let us now do that. And this is going to be very important topic because this will be the starting point for the second course on electromagnetism. That means if you are going to take a master degree program in physics, then you'll be having a paper called Electrodynamics or electromagnetic theory. So in that, the starting point itself will be the Maxwell's equation, and then we will be discussing the solution of the Maxwell's equation. That will be the objective. So therefore, the Maxwell's equations are the central theme of the electromagnetism, and therefore you have to pay great attention to learn and understand the meaning of the equations that are written down. Fine. So let us now come back to the equations of vector calculus. In the last class, exactly, I have written down this expression that the divergence of r cap divided by r square is equal to 4 pi times the three-dimensional delta function. So this is only a three-dimensional delta function because you know that del operator is in Cartesian three-dimensional. Therefore, whether it is Cartesian or not, that's not important. But in any way, it is the three-dimensional Euclidean space, and therefore this particular 3 that is there here represents three-dimensional. It is not power. It is not delta to the power 3. Okay. Instead of that, you have to say that it is a three-dimensional Dirac delta function. Dirac delta function, by the way, there is right now there is no need to worry about it, but at least the minimum knowledge that you can have is like this. The Dirac delta function will take, this is not the strict mathematical definition, but this being the first course on electromagnetism, I'll give you a minimal detail here that the value taken by the delta function will be either 1 or 0. Okay, depending on whether you are choosing x equal to that particular value. So if I am going to write down like this, if x equal to x naught, or here you say otherwise. So that means if you are going to stay at x equal to x naught, then the value of the delta of x is 1. If you are going to stay at any other place, then it will take the value 0. That is what we mean to say. But remember, let me also tell you clearly that this is not the exact definition, because this particular thing has to be defined in terms of integral. So we have to do certain definition in terms of an integral, but right now that much detail is not required for you. Therefore, for the time being, there is no need to worry. You can now consider that it is either a 1 or 0 here, which means that you are going to remove this delta cube of this r and then put a 1 here. That's all about it. So it is that is the meaning. So here there is no confusion. You are going to substitute 1 in practically. You are going to substitute 1. So there is that is the information required for the time being. This is one of the results that you have. The second result is the curl of the r divided by r square is equal to 0. These are the two results which I have written down in the last class, and now you can refresh your memory that this is the result that is required in case if you want to do some calculation. We are not going to do detailed calculation because for first course of electromagnetics, detailed calculation on proving this, how do you prove that del cross r by r square is 0? That is not our objective. In the second course on electromagnetism, yes, we have to prove this, and we will also have to define all this delta function in terms of the integral, and so the details will be done only in the next level course on electromagnetism. For now, this is the result that will be very useful in understanding how the Maxwell's equations are established. So keep this in mind. And then what happens is that, keeping this thing, let us have this is the equation number A and this is equation number B. So what happens is that if you are going to take the magnetic field, how you are going to write down the magnetic field? Exactly, we have done this in a last class, which is the Biot-Savart law. So let me write down this expression: mu naught divided by 4 pi, only due to the conversion from the what you call Gaussian to the SI units. That's why this is there. Then we have the magnetic field is basically due to the current density. It is basically due to current, And current density, you already know the relation. Okay. So current divided by the area is known as current density. So that's all. That is the definition. If how much 1 ampere current is flowing, that's fine. But in what area it is flowing? If it is flowing in 1 centimeter square plate, I have a plate like that. Okay, you can have a copper plate or whatever it is, electrically conducting material. Either it can be a plate like this. Well, you'll have to understand what I am speaking. So either it can take a plate like this, circular plate, or it can be a wire whose thickness, here you see the cross-sectional area. So that area is what I am talking about. It can be a thick wire, okay, not a thin wire, very thick wire, like a cable. If it is so, then that is the area which we are going to substitute. Okay, so if you are going to do like that, then this is known as the current density. So the current will be flowing in this direction. And coming to the symbols, you can always use I for the current and A for the area, or you will write down area otherwise. That is equal to the current density will be J. So the symbol is now clear that I divided by the area will be equal to this. And if you want to write everything in terms of proper vector quantities, then we can always write like this. You'll be having J dot ds, because area is a surface area. You remember, whenever we deal in vector calculus, the area elements are vector quantities, and therefore you'll have to perform a dot operation for that. And if you perform the integration, you can calculate the current. So what I am trying to say here is current and current density, they are the same thing, but we have to only manipulate with the area. That's all about it. So when we are writing current density, it is not something new. Ultimately, it is the current only. We are only saying that current is passing through what area. So that clarity should be there. Otherwise, whether it is passing through very thin wire or thick wire, so that has some impact, and that is why we are going to write like this. So we have J of R prime. These notations are already explained in the last class. And then we have an R cap. Then we have divided by script R square into the volume element. Okay, volume element means the entire wire that we are going to have is actually a three-dimensional structure, right? So the entire wire is the one which is the volume tau prime. Prime means the place where the currents are present, and here there is no prime. Unprime means where we are calculating the field. This particular primed and unprimed variable notation we have seen in the very beginning of this course. Okay, maybe you have to verify in the very first few lectures about the prime and unprime notation. So that should also be in mind right now. Then writing down this equation will be comfortable for you. Now, once this equation is written down, there is something interesting. You can quickly calculate, and you see that this R by R square, now you have to give your attention to the R by R square. Do you have R by R square here? It is there. See, this particular portion, you have an R, then you have a divided by R square. Then you have this cross product coming. So that means the equation number B, okay, that is going to be useful for evaluation of certain thing. Okay, that means we are going to calculate the curl of this particular quantity. Okay, so the point to be noted here is that you will be using this R by R square function, whether it is this method or it is that method. Okay, that is what ultimately I am trying to say in evaluating this particular quantity. So that is the reason why A and B are useful. But remember, once again, let me tell you that we are not going into the detailed proof of how all these steps are done. That is not there in your syllabus. That is why we are not doing. Okay, so there is no need to worry from your side also, even if you don't know the calculation. That is not there in your syllabus. But I am giving you considerable detail so that in case if you're opening a book and then reading, this kind of equations will come and you should feel more comfortable. That is the conclusion. Now, what is that we want to do is that once you have this particular Biot-Savart, so therefore I'll write down that this is BS. BS means Biot-Savart. Now you can calculate the divergence of the Biot-Savart. Okay, that is what I mean to say. This equation you'll have to copy here, and you can evaluate this, and you can also evaluate the curl of the Biot-Savart law. So basically what is done, now you can understand what Maxwell is doing. Biot and Savart, these two people have experimentally observed the force between two current carrying conductors. That is the experiment they have done. Okay, they have not calculated magnetic field directly. They are basically seeing that the two wires are either getting attracted or the two wires are repelled whenever current is flowing in the same and opposite directions. And that's all about it. And later people understood that that effect is because of the magnetic field, and then they have written down the dependence of magnetic field and the current passing through the conductor. So all these things are experimental observation. Now much later means, remember in the beginning I told some history, and these things, the Maxwell work is something like 1888, that kind of time. Maxwell has done by performing mathematical work. That means already you are having the Biot-Savart law. First of all, rewrite the Biot-Savart law in the vector form. That's what we have done in the last class. First of all, rewrite it in proper vector form like this. Then perform the divergence calculation and the curl calculation on this particular equation. That is what you have to do. And then the simplification. Of course, simplification requires some amount of doing the gymnastics with this kind of equations, equation A and B, together with additional rules of vector calculus. Okay, so you need some working knowledge in vector calculus to do the simplification of the divergence and curl. But that's what I already explained. Those steps are not important for you now. And the conclusion after doing all that calculation is that divergence of B equal to, and now you can understand from where this B is coming now. This B is basically the Biot-Savart law. And just now it was there, right? So what was there in the Biot-Savart law? This B. So this B of R is exactly what is written down as B vector for convenience. Every time you don't have to say B of R. Every time you don't have to say J of R prime. So these are convenient notation. Okay, every time you don't have to write. This entire thing you simply write down J. J means current density, that's all. And similarly, whenever you say B of R, for convenience we always say simply B. So that is why we write like this. So now you understand how this is coming. So you are actually taking the divergence of the Biot-Savart law. That's what you are doing. And then do all the calculations depending on this kind of formula. And now this is not sufficient. You'll have to do still more, apply some product rules. There are product rules are there in vector calculus. You'll have to apply that, do the simplification. And if you do all that calculation, surprisingly and interestingly, you get this result that the divergence of B equal to 0. So this is how the equation is generated mathematically. And physically, people were interested what is the meaning of 0, why 0 is coming into picture. And that physical explanation I have given in the one lecture previous to last lecture. Okay, in explaining what is known as the solenoidal field. So whenever the divergence goes to 0, such a field is known as solenoidal field, and the physical interpretation is that the field lines will be closed loop. So that is one of the interpretations and visualization of divergence of B equal to 0. And in addition to that, let me, before going to this, I will write down the name of the equation. Let me say that this is your Maxwell's equation 2. And physically, you know that this is the solenoidal field, okay. Magnetic field lines are closed loops, that is also okay. In addition to these two physical understanding, we have an additional understanding of this. What is the additional understanding is this equation or this result gives you an important conclusion. So the physical understanding of the second Maxwell equation, that means divergence of B equal to 0, is the fact that magnetic monopoles does not exist, or magnetic monopoles do not exist in nature. That is a conclusion. By that, what is the meaning of this particular statement? Monopole. What is meant by monopole is, if you know dipole, you can easily understand a monopole. In the case of the electrostatics, you already studied what is a dipole. Same concept is applicable in the case of magnetism. If it is the situation in electrostatics, then it is known as electric dipole. In the case of magnetostatics, it is known as magnetic dipole. So there is no complication. The concept is very simple. If you have a plus q charge and if you have another minus q charge, so this is plus q charge and there is minus q charge. This plus and minus should be present. Magnitude also should be equal. That is important. So if you have identical strength of the charge with a plus minus combination, and then automatically this kind of a pair. So this one is a pair, right? This pair is known as a electric dipole. So let me write down this. So you can easily understand that a pair is required and one should be positive, another should be negative. In addition to that, their strength or the value of the charge should be same value. So these are the restrictions, these are the conditions. Whether you draw the line between them or not, that is not important. Okay, the purpose of drawing this line, generally people will draw a line here. That is to tell what is the distance of separation. You don't have to draw a line. Even it's okay. If two charges are there, that is electric dipole. That's all. Why people draw the line is only to say that the distance between them is d. That's all. And similarly, so you understand what is an electric dipole. Di means two. So two of them are there. If you have only one, suppose if you have only one plus q is there, that's all. Minus q is not there. What we will call this particular thing is an electric monopole. So now the word monopole is coming into picture and there is no confusion or there is no difficulty. You can easily understand that monopole means a single charge. It can be plus q, it can be minus q. Even if a single minus q is located isolated, okay, isolated means separately. Minus q alone is located in some region of space. Then that is also called an electric monopole. So same name electric monopole, you can apply even for this. So the concept of the monopole is very clear, and the monopoles, electric monopoles exist in nature. They already exist, right? You have positive charge, you have negative charge. Both are available. You can perform experiment with that. Therefore, since both of them are available to you, the divergence in general is not equal to 0. That means, now since monopoles are existing for the case of the electric situation, that means for the electric field situation, 0 is not compulsory. See here, there is an important point here. This point, let me make it clear that when you write this 0 here, the 0 is always. This is important. Always, irrespective of how the magnetic field is coming into picture. The moment you have a magnetic field, okay, how did you generate the magnetic field? That is a different story. Okay, by some method magnetic field is existing, and if it is the case, its divergence is always 0. That's all about it. That is what it means, always. But in the case of the electrostatics, that is not the case. Because monopoles are existing, electric monopoles are existing in this particular electric situation, and so the divergence of the electric field is not 0 always. So the conclusion, please make it clear that this is not equal to 0 always. But rather, you already know that the divergence of E is equal to rho divided by epsilon naught. This is what you already know. So the point is now clear. What is the meaning of 0 and non-zero? So therefore, because now in our magnetic situation, what is happening is that the divergence of B is equal to 0 always. Therefore, we make a conclusion. The conclusion is important, that magnetic monopoles do not exist in nature. So coming to the understanding of monopole, it is very simple that if you are going to have a bar magnet, because this is the one that we can play with this, so we know very well, you have a north pole and then south pole, and when you have a bar magnet like this is called one pole. So, okay, so this north is what we call is one magnetic, let me say, instead of saying one, let me say that the north is, I'll say north is a magnetic monopole. That's all. If you say only north, I have only north means, then we say that is called a magnetic monopole. Similarly, if you say that only south is present, if you say like that, then that is called a magnetic monopole. This is also magnetic monopole. But in the case of the this kind of a bar magnet, for example, any kind of magnet, okay, you will be always having a combination of n and s. The moment you have a bar magnet, one side will be south, the other side will be automatically north. This combination is only present. That is what we say dipole. Okay, so now this combination is there, right? So this is always combined now. In a bar magnet, you have one side south and one side north. Therefore, north and the south is combined in an object, physical object. And this combined object is what is known as dipole. Two poles are there. And since it is magnetic, we say it is a magnetic dipole. In the previous case, it is called electric dipole. So the terminology is now clear. But now you can ask the question, I can always take some cutter and then cut this. If I cut it like this, I will make this into two pieces. And if you make it into two pieces, can you now ask the question on the left hand side, okay, on my left hand, I will be having north pole, and on my right hand, that another piece, you have this become two pieces, right? So you have a piece like this now, that is one piece. The second piece is there in my hand. So this will be south and this fellow will be north. Now, can you say, that is what we mean to say, can you say that we have broken the north and the south and separated each other? Is it possible or not? You can easily break a bar magnet. That is not a big thing. You can always break. But after breaking, what happens? That is the interesting point. The moment you break a bar magnet, this becomes automatically south pole. And this edge will become automatically north pole for this small magnet. You have a small bit here, right? Anyway, the right side of this particular magnet is south, same south here. But the place where you have broken, right, that becomes automatically north pole. It naturally happens. You don't have any control over that. You can't do anything to that. So that don't come here. You can't say like that. It comes, okay, whether you like it or not. And therefore, what happens is, once again, you are going to have north-south combination. And therefore, this is also a dipole. And this is also a dipole. And if you are going to cut it into, again, if you are going to cut it into small pieces, whatever small extent, to whatever small extent you are capable of cutting, nature will create automatically another pole. And then a combination always exists. So that is the interesting result experimentally. And therefore, finally, we make a conclusion that in the nature, we do not have magnetic monopoles. So that is the statement that I have written here. So now you see that the conclusion, that we have an important conclusion, that in the nature, we do not have any magnetic monopole. If at all anything is present, it should be in the form of dipoles only. So that is the physical understanding of this particular mathematical equation, divergence of B equal to 0. And this equation is known as the second Maxwell's equation. So you please don't call this as Gauss law for magnetism. Okay, some books are writing like that, but that's not correct. So this is not the Gauss law for magnetism. So there is no such name for that. But instead, this equation is generally known as the equation representing non-existence of magnetic monopoles. That is what you have to write down. Don't use the word Gauss law for this particular equation, divergence of B equal to 0. Only for the electric field equation, you have to say it is Gauss law. For the case of divergence of B, the word Gauss law should not be used. Okay, so this is the point, first point. The important point, once again, I will make you refresh your memory, that the right hand side 0 is always. Always means irrespective of whatever be the situation, whether you keep it in vacuum, whether you keep it in material medium, okay, whatever you do, whatever be the condition, under all conditions that you are going to do, 0 will be the result. That is the meaning. But in the case of the electric field, 0 is not necessary. As you see, this is not equal to 0 always. Sometimes it can 0. That is the meaning. Not equal to 0 always means sometimes it can go to 0. That is allowed. That is not a problem. So where it is allowed, I already explained, in vacuum it is 0. Okay, so that clarity also I will make this. So divergence of E equal to 0 in vacuum. So this equation should not be confused. Now, because divergence of E equal to 0, I will say that electric monopoles do not exist. Such wordings will not come because it is a special situation where 0 is present. But in general, rho by epsilon naught is the situation. So now the confusion should not come to you. Now, we are now having two of the equations right now. So your Maxwell's equation 1, you know that, and your Maxwell's equation 2. So two of the Maxwell's equations are clear to you. Okay. So one of them is regarding the divergence of E. The second one is relating to the divergence of B. So divergence part is clear. Now the next thing that we are allowed to do is regarding the curl. So we then ask the question, what about this and what about this? So we'll have to learn about the curl of these two vector quantities. I mean the magnetic and electric field. Now the answer, we can get it provided you know a theorem in the vector calculus. So therefore I will write down here. Now our objective is to learn the curl of the electric field and curl of the magnetic field. For that we need a theorem. This particular theorem is very similar to the Gauss divergence theorem that we have seen in the last class. And now this theorem is known as Stokes theorem. So I will write down that. So once again, the understanding of the theorem is quite easy. Okay, so only when you're working out some proof of the theorem and then more understanding of the geometrical properties, at that time you'll have to pay more attention to the mathematics. But otherwise, physical understanding of what this particular theorem is saying and then applying it to the what you call the electric and magnetic field, that you can easily follow now, so without any difficulties. So let us now, I will now tell what is the statement of the theorem. It says like this: if you are going to consider the curl of a vector field, you remember curl of a vector field. Mathematics doesn't say anything about electric field and magnetic field. Okay, mathematically speaking, it could be any vector field, and therefore generally any vector field is what is written as A vector. So if you are going to have a A vector, and that being a vector field, you can perform the differential operator curl. So what will be the resulting object? Curl means curl of a vector will be vector only. So this object is a vector object. Now, since this is a vector object, this has to be taken a dotted with another vector. And you know what are the possibilities? In the previous class, I explained what are the possibilities for the dotting here. You put a dot here. Either you can put a surface or you can put a length. These two things are vector quantities. Volume cannot be done because volume is a scalar quantity and this is a vector. So that is why that combination is not having interesting property. So therefore, this is an interesting property because you have a vector object on the left side, you have a vector object here, and you are taking this dot, and therefore this entire thing is a scalar quantity. So since this is a differential operator on the surface, this integral has to be a double integral because you have the surface integral, right? So therefore we can write down like this. So the Stokes theorem speaks about this. The surface integral of the curl of the vector that you are going to do will be equal to, you remove the curl here. If you remove the curl, I will be getting the original A vector and then dot. Anyway, this also is vector quantity and the double integral is going to become a single integral. That means it's a line integral. So I can write down like this, the integral over A dot dl. So the meaning can be understood like this. How do you understand this? If you are going to have something like this, some circular plate, so it's a kind of a disc. It need not be circular. It can be of any shape. Okay, shape is not important here. It's only certain area is there. This is the certain area. So is it clear, right? So I'll write down A or EA area. Some area is there. So when you have like this, you can always define what is the normal to that. Normal means perpendicular. That means for this area, you can say that, okay, this is the normal perpendicular surface to this. So therefore, that would be the vector direction. This is the direction of ds. Magnitude of ds is this one that I have put the shade here, right? That shaded region you can numerically evaluate, and that is the magnitude. What is the direction means? That is the direction perpendicular to that. Now, such kind of surfaces where you are able to define clearly the direction of the surface, such a surface is known as orientable surface. So let me write down this particular surface is the orientable surface. So this is the important restriction or condition that should be applicable. Only if you are having a surface that is orientable, then Stokes theorem is applicable. Suppose if you say, no, I have a surface for which I don't know the direction of the ds means, then Stokes theorem is not applicable. That is what I am trying to say. So the word orientable means orienting means showing the direction. Okay, that is the meaning. So you are able to show the direction of ds. That is the meaning of orientation. If you are able to do that, then we will be able to calculate the line integral of. So if you want to perform a line integral, you'll have to go along a particular curve. Some curve should be there. So along this particular line, we say that it is either line or we say whether it is curve. It doesn't matter. So line doesn't mean generally straight line. Okay, if you want to be a straight line, you have to write ST. Straight line should be there. Okay, if you simply write line, then it can be like this, because any small bit you take that belongs to the straight line. So that is why it's called line integral. So line integral doesn't mean straight line integral. It is an integral along a curve. That's all about that. Okay, now the question is, where is the curve, or where is the this kind of a line here in this particular situation? And now we are going to show where it is. Let me show that. Okay, so there is, you come to the boundary. Boundary means the last place. Can you see this line? There is a line at the end, right? That is called a boundary. So this particular line that is there, this is the boundary line. So that is called the line or the curve. So you have to travel like this. I am putting arrow here. So you have to stand on the edge of the disk, very edge of the disk. You can't even put one step this side. If you put one step this side, you will fall down. Okay, so that is the edge of that. Okay, so on the very edge you will be going, and then you'll be walking around, all around this, and then come back to the original place. So I have put a arrow here. Yeah, I have put a arrow here, right? That is the place where you start, and then start walking along a particular direction. Direction is important. And then you travel like this all the time. You'll have to walk only on the edge. You should not come in the middle while walking. That is a condition. You'll have to walk only on the edge, and then again come back to the original position. Okay, so you start here, go wherever you want, and then come back to the original place. Then it is called a closed loop, right? This is the closed. Then we say loop. Because it is closed, it's also called loop. And then when you are performing like this, that is why it is called closed integral. Okay, you complete this entire place, and then while you are performing this, you are also doing some computation, and therefore this small ring here represents it is closed, and therefore this is a closed line integral of the vector field. What is there? No, this is area is okay. In this area, what is there? In this area only some vector is there. A vector is there. Okay, that is why you are performing some calculation. And dl here, dl is any small bit. You take any small bit, that length will be equal to dl. So the ultimately what is the statement of the theorem is the following. Whether you are going to do this kind of a integration, this kind of integration means, once again, let me explain what is the meaning. There is a vector, that means certain physical vector is there, which is spread on the area A. In some area, some vector is present. That means you have electric field in some area, magnetic field in some area. That is what I mean to say. And then you evaluate the curl of the vector field in this area, and then you perform the integration on the entire surface. What is the meaning? Performing the integration on the entire surface means you will have to walk everywhere on the surface. You have to put your foot everywhere on the surface. You should not miss any point. Okay, it is like sweeping the entire area. Take a broomstick and sweep the area. While sweeping, you should not miss out any point. Completely cleaning. Okay, like that. That is what we mean to say. So if you perform like that, then it is known as a surface integral. You do that, you'll have a numerical value. Okay, you can always finish the calculation and keep a numerical value with you. And then you do another calculation. You go only along the edge like this, and then come back to the original place. And this will give you a numerical value. And ultimately, interestingly, these two values are equal. And therefore, what happens is, which integral you want to calculate, that is you can choose. That means if the right hand side integral, line integral is easier, you perform that. In case if you believe, or in case if you feel that performing the surface integral is easier, you do that. Whether you do this method or that way, you are going to get the same answer. That is what is the meaning of this Stokes theorem. And therefore, Stokes theorem is enabling you, this is important, enabling you to convert a double integral to a single integral. You see this? You can convert a double integral to a single integral, or you can convert a single integral to double integral, whatever it is, they are equal. So whenever you want, you can play around the vectors and then convert a line integral to a surface integral. So that is the conclusion. And orientable is a technical word that is entered into picture. You don't have to worry right now too much about that. But at least it is better to know that Stokes theorem is applicable only on orientable surfaces. Suppose if it is not orientable, it's quite simple. Stokes theorem is not applicable. But however, sometimes you'll get a doubt. I am unable to visualize what is meant by non-orientable surface. Okay, that's only geometrical visualization. It is quite simple. For example, if you have you take a book. In a book, you have page numbers are printed, right? You have a book like this. Okay, in the middle you have the binding. Then you have one sheet of paper. In one sheet of paper, you will be having page numbers are there. So let us say that this is page number 12 and this will be page number 13. And you can turn the paper and then write the next will be the 14 page number and 15 is another page number. So you are able to clearly tell that this is page number 12 and this is page number 13. If you are able to clearly tell which is page number 12 and which is page number 13, then it is orientable surface. Suppose if a situation comes to you that I am unable to distinguish between which is page 12 and which is page 13, if such a situation comes to you, then that particular surface is non-orientable. So automatically question will come, how a confusion will come, which one is page number 12 and which one will be page number 13. Okay, that confusion will come like this. I will give an example when the confusion will come. Now what happens is that this is 12 and this is 13 and you have a book where binding is there. That's fine. Forget about the binding. So now you have this is page number 12 and this is page number 13 you have. Confusion will come like this. Will come if you flip this. That means you twist the paper. You take this is a single paper you have. You twist it. Now you don't have a book. Okay, this is you're taken out. One paper you're taken out. Now you have only a paper like this. Now one side of this you twist and then you roll it like this and then you paste here. Okay, you can always roll like this. You simply take the like this and then roll. So it looks like something like cylindrical object. And that this is the place where page number 12 is there. This is the place where 13 is there. This is the place where 13th page number is there. I'm going to join here. But instead of joining directly, I'm going to twist it and then join it here. If you do that, then what happens is there is no clarity on which is page number 12 and which is page number 13. Now to demonstrate this, probably I will just show you how this is done. Now you see this, how paper is now twisted and then joined at the two ends. You just see this. See, instead of joining directly, you twist it and then join it. That's all. Now, if you join like this, you can't tell now which is the top surface and which is bottom surface. You see, it is twisting and then going right. The one which was top surface becomes bottom surface. When you perform a kind of surface like this, which is a complicated surface, then the orientability is not there. So now you can understand what is meant by orientable surface. Orientable surface is the one for which the direction of the ds is well defined. That's all about it. And whenever you have that kind of a strip, okay, I have shown you an example, right? That is known as the Mobius strip. It is a very simple paper and then twisting on one side and then joining them. For a Mobius strip, it is not orientable. So this is not a orientable surface. So what is the meaning of not orientable surface is that the direction of ds vector is undefined. We can't, that is undefined means we are unable to tell what is the direction. Okay, for such kind of objects, the Stokes theorem is not applicable. That is what I am trying to say. So this is all about the important theorem, namely the Stokes theorem. Stokes theorem is the one which is going to make this kind of conversion. And now, using this particular Stokes theorem, I will explain how to get the remaining two equations. Okay, we have already seen the Maxwell's equation 1 and Maxwell equation 2. Now we will have to see what are the Maxwell equation 3 and 4. For that, we will be using sometimes the Stokes theorem. So keep this theorem with you readily, and we can apply at any time as you like. Okay, now before proceeding further or before closing the topic, let us make one more small information, because the information is quite simple and you can easily grasp, and that is the Faraday's law. This is quite easy to understand. So therefore, let us do some calculation which will give you quickly, you can get one of the Maxwell's equation. So I'll explain this one. This is an experimental Faraday's law, by the way. You already know very well that the EMF generated, so this kind of symbol will be used here for EMF, will be equal to minus d phi by dt, where phi is the magnetic flux. So this is very clear. This is coming purely from experiment, and E is the EMF. So now what we will do is, we will not use the word EMF, because ultimately it's a voltage. Potential difference, right? EMF means potential difference, which means that it is a voltage. So therefore, because of this reason, we will better use the V for the voltage rather than this kind of E. Because why this is not comfortable is, we are going to write down the electric field E here. And if you also write like this, some confusion will come. So better to therefore write down that the electric potential that is generated. So V I will write down, which will be equal to minus d phi by dt. So that is how you write down. So that will be comfortable. That is first thing is clear. The second thing is the magnetic flux that you are going to have divided by the area. In the yesterday's class, I have explained why you want to divide the area, why unit area is required, and then why the flux has to be normal to the area. These things I already explained in the last class, and we already know that the magnetic flux passing through some area is known as the magnetic field. This is the magnetic field. Alternate name for this is magnetic flux density. So the magnetic flux density is a better name. So therefore we write this as B vector, magnetic flux density. What is magnetic flux density? Is magnetic flux. Magnetic flux is what you put a phi divided by the area. So I can say like this. And therefore what you do is, if you take a cross multiplication, we get B dot ds. Because when you want to write certain things completely mathematically, when you are taking a cross product, the area has to be represented by a vector quantity. So, but however, magnetic flux is a scalar quantity. So you have two vectors, and how scalar will come? Only if you take a dot product, it will come. Okay, you can't take cross product. So naturally it happens like that. B dot ds will be equal to this. So because if this is a differential surface area, automatically this also will be a differential. Okay, so if you want to get the total flux, then you will have to integrate this B dot ds. So this thing is very clear. This is very simple one, that the magnetic flux lines divided by area. That means the normal component of the magnetic flux penetrating into a given area is known as the magnetic flux density. And the magnetic flux density is what exactly we are measuring in Tesla. That's all fine. So now this idea should be clear, and we are going to substitute this expression into this place. So there is a phi here. So you bring this equation and then you put it here. That's what we will do now. That is equal to minus d by dt of the phi will be this integral of the B dot ds. That's all. And here you have the voltage. So now there is one more thing that you need to know. I'll explain. That long time back, that means I think 10 lectures before this, I have already explained that the integral of the electric field dot dl. Okay, if you do that, then this is known as the voltage. or whatever it is, potential difference. So the kind of integral of E dot dl has to be performed between two limits. Of course, some a and some b will be there. That is there always. In case if you are not having any limits, if it is a closed loop, then it is 0. So this also you should remember. These things are not new for you, because we have discussed a long time back when we were discussing electric potential. So now you can refresh your memory. Instead of the limits a and b, suppose if you have a closed loop and if you are going to have a E dot dl, then this is 0. So this is important. Okay, so now on the left hand side, do you have 0 volt? That is what you have to see. On the left hand side, we don't have 0 volts. So therefore, you should not use the closed integral. Instead of closed integral, some limits will be there. That should be clear to you. And therefore, I'll write down that there is an integral from a to b. Some number should be there of the E dot dl, where E is the electric field. And what is dl? dl is the along which you are going to perform the integration. Okay, we are going to take some wire and then come around a path and then evaluating E dot dl. It is as simple like this. It is not too complicated to understand what it is. If you have a resistor like this and then the wire comes like that and then you join it here. So what is the meaning of this is that if you are going to travel like this, then this portion is the dl, this length. And then this is the path that you are going to follow, and therefore this is the curve that you have. So the integration is going to be performed on the curve. And what is the meaning of this particular limits a and b is, it depends on where you are starting and where you are ending. If this is the starting point a, then that is the a here. And if you are going to perform the integration up to this, then we say this is b. So integral a to b, okay, that is start here, go here and then perform the integration and stop here. That is called integral E dot dl. That will give you the potential difference between the point a and b. So practically it means that in a given circuit, the potential difference means if you take a multimeter and keep one end of the multimeter here and the another end here, the multimeter will show you some voltage, right? That is what you understand. So that's the meaning, where the electric field is the electric field that is present in the system. Of course, in the system, electric field should be there. Then only all these things are meaningful. So ultimately what happens is this Faraday law that is there here has been rewritten like this. Okay, so now once it is rewritten, now it is a time to see where you can apply the so-called Stokes Theorem. So now let us apply the Stokes Theorem into the picture. So now on the left hand side, I have a line integral. You remember what is Stokes Theorem? A double integral can be converted to a line integral or vice versa. That means line integral can also be rewritten as a surface integral. So that's what we are doing. So we will now rewrite this as a surface integral. So that will be equal to the curl of the electric field, then dot ds. On the right hand side, that is equal to this expression. Let us now do the time derivative for the b. Nothing will happen for the surface area with respect to the time. You see, you'll have to be clear about the experimental system for the Faraday's law. In the Faraday's law, you have certain area and wherein the magnetic flux density is varying. So when that is happening, will anything happens to the surface area? Surface area, nothing will happen. You are only fluctuating the magnetic field. So nothing will happen to the surface with respect to time. Okay, so this will not ds by dt, there is no effect on ds by dt. So what is happening is only magnetic field will vary with respect to time. Therefore, we can write down dou b by dou t. So I'll write down like this, minus of. So let me write down this integral is there, fine. Then I'll write down dou b by dou t. And why we are converting the total derivative to the partial derivative is that out of the space and the time, space is there, x comma, y comma, z, then time. So out of the space and the time, nothing happens to the space part. So nothing happens to the area, but only to the time part only the magnetic field is varying. So therefore, it is happening partially to time only, not to the space. Therefore, this is dou b by dou t, then dot, this ds will be written down here, ds. So that means basically we are trying to say that the magnetic field, remember this once again, let me explain once again. This magnetic field is a function of x, y, z, t. Magnetic field will vary in space. Magnetic field can also vary in time. Both can happen. The meaning of this is that the magnetic field is varying in time. With respect to time only we are varying. With respect to space we are not varying. We are not varying means what? In the experiment we are not allowing to vary because you are only controlling the experiment, right? So you only change the magnetic field with respect to the time. In the space everywhere same magnetic field will be there. That is the meaning of dou b by dou t. That's all it is. And because this is a surface, as you can see that this is a surface here, whether you write a single integral or double integral, both are same. Ultimately, it has to be a surface integration. So, because left side we have written 2 integral, it will be convenient to have a good representation that the ds means surface integration. So, this is the integration has to be performed on the surface. That's the meaning. So, now you see that this particular thing is the place where you have to be careful that from here to here, when you are moving in this particular direction like this, we are using the Stokes law or Stokes theorem. That's all. On the right hand side nothing happened. Right hand side is simply copied here and we are making certain things clear when you are writing, and that's all about it. And once you do that, we are able to get the ultimate result, namely you see this surface and that surface are exactly the same surface. That is the meaning. Whatever surface you are going to perform the integration on this side, it is identically the same surface that is present in the right hand side. Because in an experiment, right? In an experiment, you show me which area means you have to show only one place. It is the same place that is represented mathematically by this ds vector and the integration. And therefore, the integral on the left hand side and the integral on the right hand side are identically the same kind of integrations. And therefore, what happens? You see that this quantity should be equal to this quantity. Are you able to observe that? That's what you have to observe. Because ds is there, dot is there, dot is there, double integral is there, double integral is there. Therefore, all the things are same. Then what is only changing is del cross E will be equal to minus of dou b by dou t. So if you observe that, because the two integrals are identically the same, our conclusion is that the del cross the electric field will be equal to this minus is there. So that should be written down. Then we have a dou b by dou t. And that's all about it. And ultimately, this is the equation that we are getting, which is nothing new. Remember, this is nothing new. This is the Faraday's law, in fact. So this is actually the Faraday's law. But however, since this has been done with respect to the analysis of the vectors by the Maxwell, this equation is known as the Maxwell's equation 3. So this is your third Maxwell's equation. So as you see, Maxwell's equations are nothing but they are some way of rewriting the Coulomb's law. It is some way of rewriting the Biot-Savart law, and now the Faraday's law is also rewritten like this. So which means that the experimental observations and the experimental evidences, the experimental data, everything is written in terms of rules of vector calculus. And now we have a third equation. This is known as the Maxwell's third equation, which is nothing but it is the Faraday law. There is nothing wrong in saying this is exactly the Faraday's law, but it is written by Maxwell. Okay, so let us therefore stop at this particular place. And now you know that we have to do the Maxwell's fourth equation. We have to do that. We will do in the next class. And once you have all the four equations together in one place, then I will explain you how to obtain the electromagnetic wave propagation equation. So that can be done probably in the next class. So these are the most important topics. And I will also explain how things are connected. So that point is also very important. So those additional discussions we will do in the next class.